Good afternoon. Hi again. I welcome those who have just joined us. This webinar is about to start, but firstly, let me remind you again some details. The question feature is available in your control panel during the whole session, and the last 20 minutes will be devoted to answer all the questions. Whether you don't have time to ask or we don't have enough time to answer all of them, please feel free to contact us at marketing@gmb.com. And anyway, speaker contact information will be provided at the end of the presentation as well. Now it is time to introduce you to the speakers of this webinar. Irma Rodríguez, who is the Division Head of GNSS Algorithms, Products and Services at GMB, and David Calle, the Section Head of Advanced GNSS Services at GMB. Now, I give the floor to Irma, who begins with the session. Thank you, Irma.
Thank you, Tatiana, for the introduction. Welcome, everybody. Thank you very much for being here today with David and with me and your interest in this webinar, Satellite Navigation to Enable the Way Forward, the Way from Science Fiction to the Next Generation of Autonomous Drive. Before starting with the webinar, let me tell you that as for the presidential debate in the United States, we have checked before coming here that we have no COVID-19, so it's perfectly safe that we are here in the same room, just in case someone is wondering what we are here together. Okay, David is him, I'm Irma, if it's not obvious. Okay, so let's start. Both of us work at GMB, so let me introduce briefly the company. GMB is an international business group who was founded in 1984 as a spin-off of the Polytechnic University of Madrid. The company offers solutions, services, products in very diverse sectors, such as aeronautics, banking and finances, space, defense, health, cybersecurity, intelligent transportation, automotive, telecommunication, and information technology. One of the things that we both appreciate most of working in the GMB team is the possibility to innovate with cutting-edge technologies in a great working environment. I think this is really important. And just before beginning with the technical stuff, let me tell you the story why David and I are here today in this webinar. It was year 1985, and there was a little boy born in Plasencia, Spain, and a little girl in Madrid, in Spain too. They didn't know each other, but they were full of dreams, many times inspired by the American series that they watched on TV at that time. I'm sure most of you recognize this picture. This is the night driver, the car who was able to drive on its own without the need of a driver. And who hasn't ever dreamed of having such a car in their life? So maybe this is one of the reasons why we decided to do engineering. And afterwards, GMB offered us the possibility to work in aerospace. David and I work in the GNSS business unit at GMB. David is in charge of the high accuracy solutions and products, and I'm the division head of GNSS algorithms, products, and services. Now I give the floor to David because he's going to explain some details about autonomous driving applications. Oops.
Okay, thank you, Irma. So as Irma has commented, I'm starting presenting a little bit what is autonomous driving. And for that, I'm going to introduce first what are the concepts and what is very important for us, which is the different levels which are currently identified by the community. So there are six main levels. The zero, let's call zero, which is the classical cars we all know, as defined by Henry Ford many years ago. And in these cars, the driver is the only responsible to control all the operations which occur in the car. Then we are introducing different features on the car. Good. Sorry. Where the responsibilities are transferred from the driver to the vehicle. Here we identify the first level, which is called also assistance, where very basic features are introduced like the cruise control, adaptive cruise control, parking assistance. And in this level, the driver must be ready to take full control of the car at any moment. The second level is the automated system. It's able to take the control of the car for various operations, including accelerating, braking, or even steering the car. In this mode, the driver shall be still monitoring the vehicle movement and be ready to intervene at any moment the control of the car and to react accordingly. So this is the level where we are mostly observing now in the streets with, different famous vehicles which are there, and you have to be most of the time of observing what the car is doing and what is happening with the traffic, and putting your hands in the steering wheel and be ready to take the control if needed. Then we have the level 3, which is the level targeted by most of the car makers right now. And this is, let's say, a big step forward. In this level 3, the ADAS system is able to take full control of the vehicle for long periods of time. And it is also able to request the driver to take control of the car if any difficult operation or situation which cannot be handled by the autonomous driving system itself occurs. So then next step is level 4. In level 4, the capabilities of the autonomous driving system are, let's say, impressive. So the driver can fully disconnect from the driving task, and the car is able to perform all the tasks under specific areas, conditions, or circumstances. If the car itself detects that the driving may be, let's say, dangerous for some reason, it is able to abort the trip, and maybe to park or to warn the driver to, let's say, to take the control of the car. And finally, we have the level 5, which is the full autonomous case, where the autonomous driving system has the control under any circumstances, weather, road, or, in any circumstances. So no need of the driver is there, and indeed, even the steering wheel is something optional. We can go to the next slide. So here we can see an example of level 4, where our night driver is taking full control of the car, while our actor, David Hasselhoff, is having a nap. Yeah. Okay, so developing an autonomous driving system is a challenge, a very big challenge. So for me, after working with the guys involved in the automotive industry, I think it's an awesome industry, because, okay, you see that there are thousands of parts in a car. They manage to have all of them ready by a certain time, to assemble them, to test that everything is ready and everything works properly with, let's say, with a very high quality standard. So for me, it's amazing. And if you have a look to the possible architecture, you can see here in the right side of the slide, there are many new things which are introduced for this autonomous driving technology. So there are many new sensors, which are hardware sensors, but they also need a very, let's say, complex software to handle all the data which is generated. So the automotive industry is also, let's say, suffering, let's say, a paradigm revolution and they are changing many of their, let's say, main attributions, and indeed they are changing from, let's say, assembling many hardware parts to also develop a lot of software, which is very critical for the autonomous driving systems. And the last part of the challenge is to produce affordable vehicles. This is very important because if I go to the car shop and I ask for the price for a, let's say, for a new car, and I want this autonomous driving capability in my car, and they ask me, okay, this is 300,000. Okay, I probably would prefer to buy a flat or a house, no? Unless I have much money. So the challenge for them is, let's say, to manage to reduce the cost of all the hardware elements and all the software which is developed to provide this autonomous driving capability and produce vehicles for the mass market. Probably you have seen in the news recently that there is a robot taxi, let's say, company located in the US, which is currently providing close to level 4 autonomy in a, let's say, in a small location, a city or a city in the surroundings. So, but I mean, they are providing these services in this small location. We don't know the price of these cars. Each unit of the cars may cost maybe $500,000. It's something we don't really know, and we also don't know the maintenance, because the maintenance is another, let's say, key topic for the mass market, because you cannot, let's say, assume, you cannot accept that your car will be in the garage every week or every month, because it is simply not acceptable by the customer. Okay, and here I'm presenting some short lines and quotes extracted from the news, which somehow translates this challenge into numbers. For example, in the top of the slide, you can see that Jaguar Land Rover, one of the car makers, is estimating that they will need around 1 billion lines of code to achieve the full automated function of the autopilot. Something similar is estimated by the IEQ. And this is not the only challenge, because you can have a lot of lines of code in your system, but you need also the necessary hardware to, let's say, to make them run and to process all the data which is received by your, let's say, your software. And it is also an estimation of the data produced by all the sensors which will be in these autonomous vehicles, and they are estimating around 2 to 4 terabytes of data every day, which is also a huge amount of data. In this plot in the right side of the slide, you can see also a comparison of what is the amount of software embedded in one car, currently modern car, without all this ADAS system. So we estimate that current cars has like 100 million lines of code. You can compare there, which is the amount of lines of code in Facebook, Windows 7, or even in a Boeing aircraft. And now we take this amount of line of codes in a current car and we multiply by 10, and we see the magnitude of the challenge, which is incredible. So this is probably one of the biggest software challenges we have faced in the last years, and we are facing for the next decade. So this is assuming in this potential architecture for the level 3 to 5 autonomous vehicle. Here we can see different kind of sensors. There are some sensors which are mainly looking to identify obstacles in the road. There are other sensors which are more focused on performing relative positioning using certain press marks in the roads or in the streets. And there are other sensors which are mainly focused on providing absolute positioning of the vehicle. So these two sensors are mainly, in this case, the GNSS and also the IMU, which is used to aid the GNSS solution. And from now on, in the webinar, we are going to focus on these GNSS and IMU sensors and how they are contributing to the ADAS systems. So I pass again the floor to Irma.
Okay, thank you, David. Well, after this very good introduction to autonomous driving, I'm going to talk a little bit about the role of satellite navigation in this world of autonomous driving applications. I don't know, maybe some of you have worked with aerospace engineers. This is our case. We are surrounded here at GMB by aerospace engineers. And I've heard many times these people who love to talk about the space and the celestial bodies, to talk about celestial navigation. This is the use or the measurements, the use of angular measurements between the celestial bodies. That could be the sun, the moon, the planets, the stars, and the visible horizons in order to fix the position. But you may have already noticed that I love history, because I've told you about the story of these little kids in Spain. I've told you about this story about the night driver, and I was investigating a little bit on the internet, and I found out that the first to navigate were the Polynesians many years ago, thousands of years ago, thanks to the use of birds, swells, and the stars, which is really amazing. Well, some years later, by the end of the 19th century or beginning of the 20th century, radio navigation started to be used. Radio navigation is the use of the electromagnetic waves in order to calculate the position. There are many different technologies who make use of these radio waves, like Lorentz radar, and many others. But the first one was the radio direction finder, with a mechanism that is very simple. With a directive antenna, you could calculate or find out the direction of a broadcasting station, and then with an additional station and an additional measurement, and with triangulation, you could calculate the position of the user, which is some way similar to the techniques that we are using today in satellite navigation. Satellite navigation, what we known as GNSS, started to be developed in the 60s in America. A satellite navigation system is a system that uses satellites to provide autonomous geospatial positioning. Nowadays, there are 4 different global navigation satellite systems. The American GPS, the European Galileo, the Russian GLONASS, and the Chinese Beidou. The principle of satellite navigation is very simple, because the satellite navigation system consists of a constellation of satellites that are indeed very precise clocks orbiting the Earth. The GNSS receiver is another very precise clock. And with that, we can obtain the distance needed by the signals to travel from the satellites to the receiver at the speed of light, so that we can calculate the distance from satellites to the user. So with trilateration, it's quite simple to obtain the position of the user. With a signal from just one satellite, we could obtain a potential sphere of locations for the user. With a second signal from another satellite, we could locate or position the user in the lines that are in the intersection of the two spheres. And with a third satellite, we could determine univocally the position of the user. But this is not that simple, because otherwise we wouldn't need tens of thousands of lines of codes in order to do satellite navigation. So what are we missing here? First of all, knowing the position of the satellites with an accuracy of 1 or 2 centimeters is not that simple. There are many effects or perturbations that need to be taken into account. On the other hand, the electromagnetic wave, the signal from the satellites, it is not traveling at the speed of light in the vacuum, but it suffers a number of degradations due to the atmosphere, like the ionosphere delay, the troposphere delay, and there are other perturbations due to the hardware delays or the local effects. In the end, we have a number of effects that could induce an error in this estimation of the position up to several kilometers. So all these effects need to be modeled or estimated so that we can very precisely compute the position of the user. Nowadays, there are many different satellite navigation techniques that can be applied. The most basic ones make use only of GNSS, the Global Navigation Satellite System signals, like GPS, GLONASS, Galileo, and so on. In this case, we are talking of accuracies on the order of a few meters. There are also several augmentation systems, like the ones used for aviation, that provide additional information on top of the navigation signals. And with this information, you can obtain better accuracy on the order of decimeters and other additional data, as for example, integrity data. And then we have the high accuracy solutions that are the ones that we apply for autonomous driving, because we need accuracies, very, very good accuracies on the order of a few centimeters. These techniques are, for example, real-time kinematics, the RTK, or precise point positioning, PPP. And apart from accuracy, there are other metrics that are very important if we are talking about high accuracy positioning and application, in particular to the autonomous driving domain. Convergence time is one of them, is the required time to reach a solution with a certain accuracy. If you look at this picture, for example, it's not the same to be able to start racing at the very first second than having to wait for several seconds in order to start running. This is something similar to the convergence time we have to deal with in satellite navigation. And the other metric that is also very important is integrity. Integrity is in some way the trust you can have on your positioning solution. For example, if you look at this picture, on the left, you have a solution that is very, very accurate, but has no integrity at all. So the risk here is quite high. On the contrary, on the right, we have here a solution that is not so accurate, but it's it provides integrity. Several situations are possible. You can have accuracy without integrity, integrity without accuracy, or ideally both of them. When talking about integrity, there are mainly two performance indicators that need to be considered. One is the integrity risk. That is the probability that the position error exceeds the out of tolerance condition without issuing an alert failure. And the other is the protection level, which is the position solution error bounding threshold for a given integrity risk. So if we look at the context right now in satellite navigation, there are many examples of applications which demand high accuracy, mainly in the professional market, Here we have some examples: precision agriculture, offshore, construction, surveying, Internet of Things, and the one that we use more at home, Pokemon Go. I think my son would not survive without this application, or maybe I won't survive without it.
Probably.
In this case, well, most of these applications demand centimeter accuracy on the order of centimeters or tens of centimeters. There is another group of applications which also demand accuracy, but maybe not so much. But it's important that the positioning solution provide some level of integrity. These applications are those in the transportation domain, mainly. Here we have the typical examples: maritime, rail, and mainly aviation, which is the domain where satellite navigation has been traditionally used with integrity. Nowadays, the usage of UAVs is also becoming quite common, and it's another domain where the use of accuracy or integrity with the use of satellite navigation technologies is also very helpful. When we are talking about autonomous driving applications, the main challenge is that we need very, very high accuracy together with integrity and without forgetting about the convergence time. So we want everything here. We have included here the typical requirements we have for this type of applications. So regarding accuracy, we need horizontal accuracy below 10 centimeters, cold convergence time below 30 seconds, hot convergence time almost instantaneous, dead reckoning, which is the capability to extrapolate the positioning solution when you don't have the GNSS signals available. So for a certain period, we need to maintain the positioning accuracy with limited degradation. And the service availability is also very high. Regarding integrity, we have to face integrity risk of up to 10 to the minus 7 per hour. And the size of the protection level is defined so that we are able to distinguish between lanes. So it's between 2 and 5 meters, depending on the target integrity risk. So what have we done to offer our high accuracy and safe solutions for autonomous driving? Well, first of all, when you're facing such a challenge, you need to know who are we dancing with. And if there is a pirouette that is needed, better to know it in advance. I was going to make a joke with the picture, but I think I will pass because David is very serious.
Please go ahead.
No, some time ago, I asked David how he was feeling as Patrick's fans. But he had to see the film, no?
I had to see the film. I don't know who is that guy.
Okay. So back in 2008, we launched our high accuracy service, Magic PPT. And we were feeling like in the greatest hit at the moment by Alicia Keys, everything's gonna be all right. We are in love with classical GNSS applications, so everything's fine. But a few years ago, when we saw the opportunity to apply this type of technologies to autonomous driving, we were feeling a little bit differently. Like the greatest hit at the moment by Imagine Dragon, dreaming about being a big star. And what were the main challenges for that? Well, we have put here the ones that we think are more challenging. No, the differences between what we have done in the past and what we had to do then to adapt our technologies to this domain. And what was more, let's say, challenging in this sense? First of all, the demanding integrity requirements that were more difficult to achieve than in other applications, let's say, the harsh reception environment, the performance of mass marketing devices, the need of integrated solutions, and, well, the road standards that a few years ago were not so well known by us. So the first challenge, the integrity requirements, because not only has the positioning solution to achieve this level of integrity, but we have to assure that we are protecting the user for any potential failure mode, including those in the GNSS satellites caused during the signal propagation, due to the reception environment, those coming from the GNSS receivers or the other sensors that are to be integrated, or those that are present in the hardware or the internal processing. Apart from that, the exposure time with a target integrity risk of 10 to the minus 7 per hour is much longer than the requirement in aviation. That means that many more things can happen during this period of time. Then, when you are driving through a highway, there are many obstacles interfering with the GNSS signals, mainly due to signs, other vehicles, buildings. So the level of multipath is much higher than in aviation applications, for example. There are also many signal reception outages due to tunnels, sign panels, bridges, overpasses. And apart from that, we have to take also into account that there could be jamming and spoofing, which means basically interference or data fake. The third challenge refers to the performance of mass market devices. The thing is that we need that the devices, the positioning solution needs to rely on comply or meet a number of requirements related to accuracy and integrity. For that, it's important to ensure that the integrated solution is compatible, and from the accuracy and integrity point of view, everything is well aligned. The characteristics of the receivers for aviation are, for example, that they are developed following specific hardware and software standards. They have extensive validation. They need to go through a certification process, and their price is very high compared to the devices that are used for autonomous driving. It's also important that the integrity performance must be assured not only through the process of developing the hardware and the software, but also that the device is able to react in a certain way in front of hazards or external failures. The fourth challenge is related to the need of integrating the solution with other external parties, because the positioning engine is not a standalone. It has to interfere with other sensors. It's integrated in a hardware platform. It also interacts with the software of monitoring and control, receives data from the correction service, uses the input data from the GNSS receivers. In this sense, it's important that all the interfaces are very well defined and agreed and aligned. The standards must be the same, or at least compatible. We also need that everything is very well synchronized, because errors in time means a very big error in position. And also, well, the different performances need also to be aligned so that the final positioning solution has a good performance. And finally, well, there are a number of road standards that need to be followed. I have included here the three of them. We have the ISO 26262 for in-car functional safety. SOTIF, the ISO 21448, and for cybersecurity and security measures, the ISO 21434. So now I give the floor again to David, who's going to tell you how exactly we have faced all these challenges and some more details about these standards.
Yeah, thank you, Irma. So yes, I'm going to introduce a little bit our safe and accurate GNSS positioning for autonomous driving. And I'm going to present it, or to introduce it in probably not the most marketing-oriented way. So I'm going to start with the standards. So I promise you, I will not. I will try. I cannot promise or commit to not bore you a lot. Then we will see the importance of the validation and simulation within all the, let's say, the development process. And finally, we will see what is the solution itself, okay? So as Irma has commented, there are three main standards, the functional safety one, the SOTIF, which is the functional for the intended function, safety for the intended functionality, and finally the ISO for automotive security. So I will review quickly the objectives proposed by each of these standards, which are followed in our development process, and also how the standards and how we are, let's say, executing all the process and generating the work products proposed by these standards. So let's start with the ISO 26262, which is the well-known functional safety in the automotive industry. I mean, this is well-known because it's applied for a wide range of systems, software, hardware applications developed in the automotive industry. And the goal pursued by this ISO standard is to avoid having systematic failures in the system. It means that there is no systematic failure in the hardware, in the software, in the design, or in any of the steps of the development, or even the validation tools. It also pursues to avoid having random hardware failures by designing the system. It means you have to implement different mechanisms at design level, for example, having redundancy or mechanisms of detection of a problem, and try to, let's say, to revert the problem somehow, or to warn the system. And finally, it has another goal, which is to control the time of exposure to a certain risk by limiting the time to react against this risk, and also defining the way the system has to react in case of detecting these failures. And how is this proposed to be achieved by the standard? So it is let's say, a very controlled process. What does it mean? It means that the ISO is very well described in the sense that all the work products which has to be generated along the whole process, including the verifications of the requirement, verifications of the design, the generation of the technical safety concept, the safety plan, how to, let's say, cover with unit testing, integration testing, error injection, everything is defined. And you have to follow the whole process, generate all the work products proposed by the ISO, and following it, you should be able to achieve a maturity level according to, let's say, the specification of your system. The maturity and robustness level and its reliability depends on the target use of the system. For this, the ISO also defines different levels, which are called ASIL levels. The most critical one is the ASIL D, which is let's say, the most challenging or stringent one in terms of, let's say, completing the process, because you have to cover a lot of things. And then we have two steps below, which is ASIL C and B. And in these steps, B and C are let's say, the position engine applications we are developing. And then below this, we have what they call the QM versions. Okay. The second standard is the SOTIF, also called Safety of Intended Functionality, which is not as well known as the previous one, also for the automotive industry. This is not a standard yet, it's a standard under consolidation, so they are still working on the definition and consolidation of the standard. And this, let's say, close to what safety is known as concept in the aviation domain, for example. The main goal of this SOTIF standard is to complement the ISO 26262, because with the ISO 26262, what we achieve is having, for example, a system, a hardware, a software, which itself is very reliable, but it do not really care of what is happening around. All the, let's say, external conditions, environmental conditions, which is not a failure in the chip or in the system per se, has to be also considered in the autonomous driving, let's say, environment. No? Indeed, a good, let's say, a good example is what happens if you are in an autonomous driving car. You have all your sensors. There is no apparent error in any of the sensors, but there is a strange object in the road which cannot be identified by the cameras or the imaging processing. So at that point, your system has to decide what to do. If brake, trying to avoid the collision, just neglect it. So they are, let's say, not errors per se in the system, but some things which, several things which may occur and has to be also well controlled. And for this, what the SOTIF standard proposes is to, let's say, divide all the spectrum of possibilities in 4 main areas. First, we have what they call safe areas, known and unknown, which is the green part in the figure you have in the bottom side. These safe areas are fine if known or unknown. There is no risk of damage in these cases. And then there are other two, which is what they call unsafe unknown. Okay, this is a not so bad area because you know that you are not in a safe situation, but at least you know it. And the other area is the unsafe and unknown, which is again, here we have a red light because we don't know where we are and it can be also unsafe. So for this, what the SOTIF standard proposes is to define and specify new mechanisms to be implemented in your system to try to reduce as much as possible when you are in unknown and unsafe situations. And this is what you can see in the figure. So for this, what we are doing in our process is identifying all the possible errors, which, or not errors, but cases which may let's say, affect the functionality of our positioning engine application, introducing monitors, introducing new requirements in the system, and implement them to control the reactions and behavior of the system. And finally, the security standard. So security is also critical for an autonomous driving application because even if you are at your house and a hacker can control your valves, it can annoy you, but just annoys you. Okay, but if a hacker takes control of your car, you can have an accident or
break the law.
No, I mean it's not a good and desirable situation at all. So that's why there is a standard for security also defined in the ISO. Here, what the standard proposes to achieve the security by design. No, and how we follow the standard. The first step is to identify all the possible threats which may affect our application, our system, identify the attack vectors, and let's say determine which are the real vulnerabilities and potential damage due to these vulnerabilities. Based on this analysis, a quantification is done, and we have to define a set of countermeasures to be implemented also in the system as new requirements, specify them, design them, introduce them in the system to reduce the likelihood of having a successful attack, which can take control of our system, and up to an acceptable level. And in parallel with this, we are, let's say, of course, performing different security-related activities like security audits of the code, performing periodic pen testing for the system, having software patches, etc. And that's all for the standards. So I have tried to be very synthetic. And the second, let's say, pillar for our application is the verification, validation, and simulation-related activities. So here, we are attacking it following 5 different approaches. First one is the development process itself. This is mainly driven by all what is written in the ISO, so we have to cover with UTs, ITs, all the verification steps, and so on. Then we have to complement all these activities with real driving tests. I mean, we need to demonstrate the capabilities and the functionality of our positioning engine application. And it also allows to, let's say, perform some data and RF sensor data recording and replay for, let's say, to repeat the process as many times as needed for real data. But for the SOTIF, as you may have inferred, there will be a lot of situations which cannot be covered by real data. And in these cases, we need to create models for the different, let's say, threats which may occur to our system, to control them and to test that they are well managed and mitigated in the system. And for that, the data simulation is really critical. I mean, data simulation and also complemented with sensor simulation, which in our case, for our positioning application, is really critical as it allows us to generate GNSS RF signals, which is basically required to, let's say, to feed the measurement engine application, covering nominal cases, non-nominal cases, and as Irma has said, spoofing and jamming, which is one of the big security concerns which are on the table for any GNSS application in the next years. And finally, we have the statistical validation. Statistical validation is a critical asset for our safety validation. Again, you need to, let's say, to validate all the SOTIF, all the possibilities which may occur to your system. You need to use simulated data. You need to use statistical validation because otherwise you would need a huge amount of data, and you will be recording data for, I don't know, it's probably 1,000 million of kilometers or something like that. So it's a huge amount of data, and also a huge amount of time, so many years with many cars driving all around the world. And finally, I'm going to present our solution. So our end-to-end solution starts by having a global GNSS station network, sparsely distributed around the world. And then we have more dense attention network in the service areas. All the data of this station network, these monitoring stations, are provided to our processing centers, where we perform our, let's say, calculations to, let's say, to provide the necessary information to, for example, position the satellites with 1 or 2 centimeter accuracy, as Irma has commented before. And this information is then provided to through the communication link to the car, where our positioning engine embedded application is running. Okay. It's also good to mention that our processing centers are redundant in different locations to ensure the availability and also all the safety measures. And they are developed also, even if they are not embedded in the car, following the standards we have commented. So we have the correction processor, which is, let's say, a QM part of the system, but then we have the safety processor, which is developed according to the ISO 26262, also following the SOTIF, and the security for automotive standard. And all the data which is generated by the safety processor is then passed to the delivery chain to make it available at vehicle level. And on the positioning engine side, we have our application, which currently is a positioning engine application developed in a couple of flavors. So it's an AutoSAR application, but also it's a Linux-based application. So if anyone is interested, do not hesitate to contact our marketing department or us directly for them. And it is able to consume GNSS plus IMU data for aiding during the reckoning parts of the road. But it is also capable of processing information from other sensors like odometer or wheel speed sensors, which may also contribute to improve the solution. As commented, we are following the three standards, the ISO 26262, ASIL-B level, where we target this software faults of 1 to -7 per hour. The same for the SOTIF. And we have also followed all the process of the security standard, especially cover the part for jamming and spoofing. So we have dedicated monitors and checks on our system to identify, detect, and, if possible, mitigate this kind of attacks. As commented by Irma, we have the fast conversion capability, which is a key feature for success. Otherwise, an owner of a car cannot be waiting for 10 minutes in the morning before going to work, even if he can be sleeping in the car. And we have also our, let's say, protection level generation capability. As Irma has commented, the idea is to have an error bounding around the car to ensure that the maximum error is not beyond a certain limit. And here, I'm almost finishing. We have some results of our positioning engine application. These are results accumulated during several thousand of kilometers of driving tests using a mass market GNSS receiver, antenna, and IMU. So the cost of all the elements is not beyond the 100 or 100 something euros. So it's something really cheap, and according to what a car maker can spend on this kind of, 100 buying one or two. If you buy a million, it's much cheaper, of course. So we have installed in the car this setup, and we have a trajectory system to calculate the reference trajectory to, let's say, to determine what is the error in each of the moments of the driving. Saying it, let's say, or summarizing this long work in in a nutshell, we are currently targeting 25 centimeters, 95% of the effort, and for the 99.7, which is almost all the cases we have faced in the roads, we are below the 50 centimeters. Okay, which is I'm really happy with these results. Okay, that's I think all from our side. This is our, let's say, our test car. We're also very proud of this. And some of on the right part, you can see one of the applications we have to, let's say, to monitor the status of our system when we are performing our driving validation campaigns. So after that, I think it's all from our side. It has been a pleasure to take your attention and to share with you this information.
Thank you, Irma. Thank you, David. Well, we have reached the closing time of the webinar, but I'm sure that we have a few minutes, if you can, to answer briefly a few questions. I don't know. Yes, we have enough time, no? I think yes, just a few minutes. And we'll start with the, yeah, we'll start with the first one. Luis asked us about the solution you are describing for autonomous driving. Is it already operational or is it still in testing phase?
Well, the solution for autonomous driving is fully operational in its functional mode. So we have already a version which is able to provide the performances that David has presented. But the final version, complying with all the standards that David has mentioned for safety, will be ready next year in 2021.
Okay. And the second one, Egeman wants to know more about how do you achieve the assurance for this process?
Okay, so as I have commented, we have applied these three standards. We have a dedicated team, experts on safety. We have targeted of the different work products imposed by the ISO 26262. And they are, let's say, iterating with our customers to try to, let's say, to cover all also to consider all the external elements which are part of the system. For example, we are developing software, but the software has to run on top of a hardware. The hardware requires also to commit to a certain assurance level. The same is happening with the measurement engine or the IMU. All the elements there has to, let's say, commit somehow onto a certain safety requirements. Not only the ISO, but also to the SOTIF and the security standards. On our side, we have followed the process. We have a dedicated team for safety-related aspects covering the ISO and the SOTIF. Also, we are performing these verification reviews and everything as the ISO and the SOTIF are proposing. And for security, we have another group of experts on security covering all the steps which are followed by any data or any communication or even the system themselves, part of the end-to-end system. I hope this answers your question.
Yes, Egeman wants also to know what is your vision of adapting these standards to aerospace sector with respect to your experience in automotive sector. Sorry.
Well,
it's a tricky question, and we have had many discussions in the past.
Well, I think that for aviation is going to be difficult. If we are talking about the aerospace, it's a different matter. In aviation, everything is very well established. The standards are very consolidated, and I think there is not so much room for changing here. But for aerospace, I think this could be quite applicable. But there may be other things that would have to be taken into account. at least regarding the technical safety concept in the end has to take into account everything that is around the element which is providing safety. You need to take into account all the interactions, all the interfaces, and this is the difference between different type of contexts, that the setup is different. But if you apply the same standards to different setups, in some way they could be adapted.
Yeah, in terms of a standard, I think for aviation there is one, which is the RTCA, which is the only one which basically covers the part of the hardware software development and also what is the SOTIF part in the automotive language. And in automotive, what we have is this divided like in 2 or 3 parts, as we have commented. But in essence, let's say in essence, or the final end, it's basically the same.
Yes. Yeah, in fact, the expertise that the GMB had in aviation previously to adapting this kind of technologies to autonomous driving was really valuable because there were many things that we already knew at that time about safety and integrity, and it's true that it's not completely or exactly the same, but it's in some way equivalent.
Okay, we have 2 more questions. I don't know if you prefer to answer by email or we have enough time.
There's one.
Just briefly. Okay, Alejandro said that precise point positioning converts time is supposed to be longer than RTK. How much time is it for PPP? And in this converts time needed to be weighed each time the car switch on?
Well, it's true that a PPP classically needs more time to converge than the RTK. But the technology we are using right now is not only PPP, but it's a classical PPP for the computation of precise orbits and clocks, complemented by atmospheric information coming from a regional network of reference stations. So it's what some people call PPP RTK. And with this kind of processing, we are able to achieve almost instantaneous convergence.
Yeah, as Irma has commented in the requirements we are receiving from the customers, it is in the level of 30, 40 seconds. So
yeah.
By that time, we are in the target performance.
And the car, I don't know if the car needs to be switched on, but at least the receiver, the GNSS receiver, needs to be working.
Yeah, and the communication with the
communication, yeah.
module.
Okay, so thank you. I'm afraid we finally reached the time and we exceeded it. So I know there is more attendants who are asking questions. Apologize for not answering it now, but we are going to answer you by email if you don't mind. And as I said at the beginning, you can reach us as shown on your screen with David and Irma email address, and also at marketing@gmb.com. Moreover, on behalf of my colleagues, I would like to invite you to answer a survey you will receive in the follow-up email later today. And finally, we want to thank you for taking time out and being with us here today. We hope you enjoyed it. Bye and see you soon next GMB webinars. Thank you.
Bye.
Thank you. Bye.